Warning! The video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. We now begin our venture into applications of differentiation. You should already be pretty much an expert at how to take derivatives and the differentiation techniques. You should have covered all of that stuff. So there should be no question about any type of differentiation that happens when we move forward. What this chapter, if you're in that's using the same textbook that I teach out of, which is a Stewart calculus textbook, or pretty much any textbook in calculus, they all follow the same kind of formula. This chapter or this unit of materials dedicated as to applications of differentiation, just like it says, but mostly to graphing. You're just trying to figure out the relationships between derivatives and graphs of functions and developing a little more theory behind the scenes. So this specific lecture and the next one after it is really focused on maximizing and minimizing function values, finding the greatest function value or the least function value if you can. And we're going to start this with a talk about local extrema. So I have the definition here, and local extrema, by the way, go by a couple different names, local or relative extrema. So we're going to let f be a function defined on an open neighborhood D. Now I didn't paste in the definition for neighborhood, but it's an open interval centered at a value, which most intervals would be, right? So you have some interval from, let's just say A to B, all right? So you have an interval from A to B. It's an open interval. That's what's critical. And suppose that you have some number c that's in that interval. Then f of c is called a local maximum, or some people call it a relative maximum, of your function f on the interval d if f of c is greater than or equal to f of x for all x in that interval. That is, you have some function value. So let's just create an interval from a to b. And let's suppose that we have some function does that type of thing. Then this value right there, notice it is greater than, that y value is greater than or equal to all y values in that open neighborhood. So we would call the point c, well, we would call f of c the local maximum, or a local maximum. So that would be a local maximum because its y value, its function value, is greater than or equal to all neighboring points. And likewise, f of c is called a local minimum on an open interval if the function value at c is less than or equal to f of x for all x in that interval. So for example, kind of looks like, well, maybe not. Maybe I should draw this a little deeper. Let's pretend this dipped down like that. Then this point right here, D, which is D comma f of D. F of D would be called the local minimum on that interval. Now, as we learned way back in the beginning of calculus, neighborhoods can be as small as we want them to be. So it doesn't have to be super sizable, this neighborhood. I could zoom in, and this interval right here would be an open interval from left to right, and that still would be a local maximum there. But anyhow, that's just a little aside. There are some vital details. I'm just reading this from this paragraph below. There's some vital details about this definition that we need to focus on. And these are things that I think tend to throw people off. So the first one, the need for our interval to be open. It is critical that you have an open interval. So when I say, like, I'm looking for a local maximum, the open interval definition is critical. And part of that definition is that f is defined on that open interval. So what does that mean? What are the ramifications of that statement? Well, the ramifications of that statement are things like this. So let's suppose that we have an interval, again, from A to B. And let's suppose that our function looks like this. That's our function, just it. Okay. Well, the problem is f is not defined on that entire interval from a to b. Also, f is not even defined. So a lot of people would think like, oh, that's the local maximum because it's the highest point on the curve. But that's actually not true because the function's not even defined there. So then people will say, well, what about right here or somewhere near to there? That must be the local maximum. Well, not really, because part of the definition requires that we have an wiggle room on either side. So let's kind of zoom into that a little bit more. Let's suppose that your function looked like this. It was open at this endpoint. It actually could be open at this endpoint too. It doesn't actually matter. But some people will claim that this is a local maximum. Again, edge points cannot be local maximums because your function has to be defined on both sides of the point and at the point. Now, to me, that sounds very confusing, so I think I'll just say it this way. I'm going to scroll up here and I'm just going to say, local extrema require that the function exist on both sides of that point that's in question. And 2, this means that endpoints of domains cannot be local extrema. So if I'm looking at some function on the interval, let's just say f of x on some interval, let's go from 1 to 10 or something like that, then the edge points 1 and 10, those cannot represent local maximums or minimums because the function f of x isn't defined to go beyond 10 or below 1. So because of that, edge points are never going to be considered local extrema. Okay, that's just critical. That's a part of this definition that often gets lost, and I'll try to repeat that as we move forward. So if that seems really wonky to you right now, no biggie. We're going to move forward and clarify that as we move on with other examples. The other issue that is kind of a weirdness about the definition is that there's a strange consideration with the inequalities. They're not strict inequalities. What do I mean by that? Well, we have a local maximum at C if f of C is greater than or equal to f of x on that open interval. Well, let's just showcase an extreme example of how broken, it's not really broken, but how weird that definition is. So an extreme example would be a horizontal line. So let's consider this line right here, the line y equals 5. And let's just limit it to go between 10 and let's just call this point down here -2. Okay, so between 10 and -2, that's all I really care about. And I want to know, what is the local maximum of that function from the interval on the interval -2 to 10? So find local max, and I call L max local max because you're going to be writing that quite a bit. So I just use L max. So find L max of this function of y equals 5 on the interval -2 to 10. Well, it turns out, by definition, if you have a local maximum at a point, then its y value is greater than or equal to all neighboring y values. Well, I hope you would agree, just scrolling down, I hope you would agree that the y value right here at, let's just say 3, the y value right there is 5. I hope everybody agrees with that. And I hope you also agree that that height of 5 is greater than or equal to all neighboring heights. It's actually equal to all neighboring heights. So it turns out 3 is a local maximum, but so is 2.9 and 2.8 and 2.7 and 3.1 and 3.2 and 3.3. In fact, everywhere on that line from -2 to +10 is a local maximum. So the local maximums, L maxes, are all x values in the interval from -2 to +10. Notice I'm not including the edge points because you need the function to actually be defined on either side of a point to be considered a local maximum or local minimum. And at 10, our function just falls off the world. It doesn't exist there. So we cannot look to the right to see, is this height higher than the height to the right? You just can't see. So therefore, we don't consider the edge points there. All right. So that's a weird thing. Also, something else, every point is also a local minimum. That is, every y value on this line is below or at the same height as all of its neighboring y values. So therefore, the local minimums of a line, by definition, are all x values, well, for this line specifically, between -2 and 10. So that's an extreme example that you really won't have to deal with, but that's just something that you need to be aware of because it does kind of creep into conversation as we move forward. The main thing, though, is just to note that edges cannot be local maximums, nor can they be local minimums. Now, I'm sure, as usual, I overcomplicated that, so let's go ahead and take an example here to clarify. Now, this is really grainy, so I'm going to go ahead and just draw over it so that it looks a little better. It looks pretty terribly grainy, doesn't it? So I'm drawing over it, trying to make it look a little better, but I don't know if I'm succeeding. These are open holes, and yeah, anyhow. All right, so use the graph to state the local maximum and minimum values of the function. Now remember, a local maximum or a local minimum require a neighborhood about our point. So do not think, let's see what our x values are. These are x values are 0, 1, so this is 2, 3, 4, 5, 6, and 7. Don't think that at x equals 0, we have a local minimum. It is not a local minimum because it's an edge point of our interval. So this point, if you're standing right here and you look to the left, you do not have a function you're looking at. So this cannot be a candidate for a local max or a local min. So that is out of the question. Now, if I decide, well, let me look right here at this green dot. Let's suppose that I'm looking right there. I have to make it kind of big so I can erase it when I'm done. But let's say I'm standing at this green dot. If I look to the left, well, this green dot is higher than all of these y values. But if I look to the right, it's lower than all of these y values. So therefore, that point is neither a local max nor a local minimum. Now, if I move on and look at x equals, what is that? X equals 1. If I look at x equals 1, the function value is actually right here. Now, if I look to the left, all my y values are above me. If I look to my right, all my y values are above me. Notice how I'm personalizing this by saying above me, below me, that type of thing. Anyway, because of that, that function value at 1, f of 1, is less than or equal to all function values in a neighborhood about 1. For x in a neighborhood, I'll just say delta, 1 minus delta to 1 plus delta. 1 minus delta to 1 plus delta. So in other words, we have a small wiggled neighborhood about x equals 1 here. And in that small little neighborhood, all the y values seem to be above f of 1. So therefore, f of 1 is considered to be a local minimum. So I'm going to write that off to the side here. Local minimum, L min, is the point 1 comma, and let's see what the y value is. That's 1, 2, 3. 1 comma 3. So we have a local minimum at x equals 1. Its value is 3. In fact, that's kind of important. So I'll say local min at x equals 1. Its value is 3. And it's just important for me to give both of those, that verbiage in both those ways, because some people have instructors that insist that students write it this way. We have a local minimum at this point, and its value is, the value of the local minimum is the y value. And the local minimum occurs at the x value. Minor little definitional items. If I keep looking on this and going to the right here, so I'll just keep going to the right along this curve, you'll see we reach a local minimum. We know it's a local minimum because that point, that y value, is below or at the same height of all y values near to it in a neighborhood around it. It doesn't have to be, so somebody could say, well, what if my neighborhood's this big? No. That's not how it works. It's a local minimum or a local maximum if I can create a small enough neighborhood so that all the y values in that neighborhood are at or above that point. That would be a local minimum. And I made a neighborhood small enough so that could happen. So that is a local minimum. So we have a minimum at 2. So local mins, we have another one at 2 comma, and the y value is 2. So again, local min at x equals 2, its value is 2. Now I keep moving to the right, and you can see it's just climbing. None of these are maximums until you get to this point right here. Definitely have a local maximum. If I put a little neighborhood, if you can imagine a neighborhood of x values, even though that's not the x-axis, you just have a little neighborhood, let's just say. That y value is at or above all local y values. So that y value is a local maximum. So we have a local max at, what is that? X equals 4, y equals 4, 5. So let me write out the words for that. So I'll zoom in here. So we have a local maximum at x equals 4. Its value is 5. Keep going to the right there, and you can see we have another local minimum. Notice the function is not differentiable there, right? You should already know why it's not differentiable. It's got a kink or a cusp there. So because that is not differentiable, well, that means nothing because we're not talking about differentiability. All we're talking about here is that a local maximum or a local minimum? It's a local minimum. So we have a local minimum at 5, 3. I'll just include that in my list here. So a minimum at 5, 3. Again, x equals 5. It's a minimum. And its value is 3. There we go. Keep moving along. Well, look at this guy right here. If you're standing right there and you look to the left, all points are below you. All y values are. If you look to the right, all y values are below you still. So that's a local maximum. Notice how I say that because it makes make sense. You know, if you're standing at that point. So if you're standing on this dot right here and looking to the left and to the right, you are above locally all other points. So that is a local maximum. It occurs at 6, 4. So local max at 6, 4. Again, at x equals 6, its value is 4. All right, just do that. By the way, taught this enough. I know somebody's going to ask, well, what if I want to stand here? You would fall through the earth because the function is not defined to have that y value. At x equals 6, the function value is there. So you have no function to stand on right here. So just be aware of that. And then finally, if you move to the right, you might say, I have a local minimum right there. I would say you don't, because you might say, well, I'm not standing at 7. I would say, okay. You say, I'm standing at 6.9. X equals 6.9. And so the local minimum is 1. And I would say, no, because that's not what that function is at 6.9. And you say, well, fine, I'm at 6.99. I say, sorry, but that's still not 1. And you say 6.999. I say, it's still not 1. You see, to have a local maximum or local minimum, the function actually has to reach that value. And this function is not going to reach a height of 1 right there. It's going to get really close, but it's never going to touch a height of 1. Moreover, at 7, the function does not exist on both sides. So don't include that edge point. It cannot be included. So that's a full example of finding local maximums and local minimums given the graph of a function. Notice discontinuities. We had a discontinuity right there, a jump discontinuity, or a removable discontinuity, I should say. And that removable discontinuity still was a local minimum. So it can happen that you have local minimums and local maximums at jump discontinuities, removable discontinuities, all that stuff. So more of a theoretical or conceptual question. Do you think it is possible for an increasing function to have a local extreme? In other words, a local maximum or a local minimum? And this really truthfully depends upon how you define an increasing function, because some people will define an increasing function to be this way. Now, I'm going to erase this because this is not how I'm going to define it. But some people will define increasing to be that we know our function is increasing if f of x sub 2 is greater than or equal to f of x sub 1 if x sub 2 is greater than x sub 1. That is a definition of increasing, but it is not the definition of increasing. It's actually somewhat incorrect, because with that definition, a constant function would be considered as increasing, and that doesn't work. But I've actually seen this definition written in textbooks. It's terrible, terrible, terrible definition. So if you have a textbook that has that definition, throw it out. It's worthless. That author needs to rewrite a textbook. Instead, we're going to say that a function is increasing if, as x increases from left to right, the y values increase from bottom to top, I guess. So that is f of x sub 2 is greater than f of x sub 1 as long as x sub 2 is greater than x sub 1. That's how we'll define increasing, which basically means it's got to look something like this. It can't flatten out. It can't do this. Okay, so this would be our definition of an increasing function. Basically that the derivative is positive for all on the domain of the function. So is it possible for that increasing function to have a local extreme? And I hope you would agree with me that it is very impossible for an increasing function to have, to have a local extreme. You could try to get really creative. I've had students that do this. Well, this is increasing, but let's suppose that it's like this. And then it does this. Well, it still has to increase because we said it's an increasing function. So if you're standing at this point, you look to the left, yep, you're above every point there. You look to the right, you're below every point there. So again, you're not at a local maximum, nor are you at a local minimum. Other students will do this. Well, what if we had something like this? And they think they're being cute, or maybe they go the other way around. Let's say that this is the open point and that was filled. They say, if you're standing right there and I look to the left, I'm above every point. And if I look to the right, I'm above every point. I would say, yeah, but that's not an increasing function, because there's a point on this function where the next step you fall. And that is anti-definition of increasing function. So that would not be an increasing function. Yeah. Even though technically the derivative is positive almost everywhere, but the derivative does not exist at a jump discontinuity like that. So it's not increasing by our definition. So the answer to this is nope, it's not possible for an increasing function to have a local extreme, just like it's not possible for a decreasing function to have a local extreme either. Really kind of a cool theoretical question now. So I challenge you to try to make a function that is increasing that has a local extreme. It would be impossible. But actually, I'm okay if you try to prove me wrong. So this section was titled, what the heck was it titled? It was titled something like Local Extrema, Critical Points, and Fermat's Interior Extremum Theorem. So now we're up to critical points. These all tie in together, by the way. Everything that we're going to be talking about in this unit of material ties beautifully together, almost everything. So a critical point. This is a very definitional statement, obviously, because it's a definition. But we're going to talk a little bit after I read the definition about discrepancies between authors and their definition of what a critical point actually is. So C, if it's in the domain of F, and either f prime at C is 0 or f prime at C it does not exist, then C is said to be a critical number. So only two conditions, one of two conditions has to be met to be a critical number. Either f prime of C is 0 or f prime at C does not exist. Okay. In addition, The point c comma f of c on the graph of f is called a critical point. That is, if c is a critical number, then its corresponding point on the graph is called a critical point. Some people call, by the way, the critical number a critical value. So if you read that in a textbook or online homework or something like that, you're doing homework and it says state the critical values, they mean critical numbers. Now here's the deal. As a theoretical aside, the definition of a critical point here is highly dependent upon the text and the author. They all agree on one thing. A critical point or a critical number is a value of c for which f prime at c is 0 or f prime at c does not exist. However, some mathematicians will argue to include endpoints of closed intervals in the definition of critical points, but this is not the definition I'll be using. The reason why is because if you have a closed interval, let's say it looks like this, you have some function on this closed interval, right? Technically speaking, the derivatives at these edges do not exist. It is true. I will 100% agree with that, unless you allow for single-sided limits, which actually do exist, right? That's what a derivative is a limit, and we can actually talk about single-sided limits. So I can say, you know what? Let's consider the single-sided derivative on this side. Now, with that consideration, we're really kind of blurring the edges here, and we might say, well, that derivative exists, or we might say that derivative doesn't exist. So it just depends on how we want to approach it. So instead, I'm just going to tell you, we're not going to consider endpoints to be critical numbers. Okay? That's just, I'm not going to do that. It doesn't really make that much of a difference. So if you have an instructor that says your endpoints are critical numbers, fine, whatever. That's not that big of a deal. It does kind of match the definition of the derivative not existing, but it also doesn't. So I'm just going to go ahead and stick with how I've always done it. The edge points of a closed interval will not be considered for critical numbers. So that being stated, if we have that same exact graph again and we say what are the critical points, we're really again looking, where does f prime equal 0 or where does f prime not exist? And again, don't include endpoints. So I will circle or maybe highlight, that's what I'll do. I'll highlight the points where I can see the derivative does not exist. And I'll highlight the x values, by the way. So here's our x-axis right here. And I will just write in that this is 2 and 3 and 4 and 5 and 6 and 7. And now we'll talk about what x values or what our x values are that are critical numbers. So for example, 1's a critical number. Why? Because the derivative at 1 does not exist because it has a jump discontinuity. F prime at 1 does not exist. Remember, derivatives don't exist when you have a discontinuity. Okay. Specifically, if your function is differentiable at a, it's continuous at a. There you go. So let's see, where else do we have the derivative either being 0 or not exist? Well, you could see that at x equals 2, the derivative, I need a different color. At x equals 2, right here, the slope of the tangent line right there is 0. So x equals 2 must be a critical number. Also, x equals 4 because, again, the slope of the tangent line at x equals 4 is 0. Basically, whenever you have a horizontal tangent. But also, where you have kinks, cusps, corners, or jump discontinuities, you also have critical numbers. So 5 would be a critical number because we have a corner or cusp there. And then we have a jump discontinuity at 6. And 7 is the edge of an interval, and edges or edge of domains, we do not consider those to be critical numbers. So our critical numbers, I'll write out as a list. I need the screen kind of somewhat visible. The critical numbers are x equals 1, 2, 4, 5, and 6. And again, if you have an instructor that says closed endpoints at an interval can be considered critical numbers, then fine. X equals 0 is also considered a critical number, but I don't do that. And then the critical points are just the points. So there are critical points: 1, 3, 2, 2, 4, 5, 5, 3, and 6, 4. Something I want to draw your attention to. I'm going to hop back a couple pages actually, I don't need to do that. Let me just showcase something to you. Notice I'm going to go ahead and circle up where we had local maximums or minimums. We had a local minimum at 1. We had a local minimum at 2. We had a local maximum at 4. We had a local minimum at 5. And we had a local maximum at 6. Now, do not be deceived here. Having a critical number does not beget immediately that you have a local max or a local min. It's just that it's part of the condition necessary to have a local maximum or a local minimum. So again, I don't want you to assume this, so I'm going to write this in red. While it's tempting to believe, it is not true that critical points are not always local extrema. They are often local extrema, don't get me wrong, but they're not always local extrema. And actually, I think my next two examples kind of delve into that. So let's go ahead. No, they don't. So let's go ahead and just show you what I mean. So let me say, let's suppose that we have a function that looks like this. It flattens out momentarily and continues up. It's called y equals x cubed or something like that, right? And notice right here, let's just pretend that f prime is equal to 0 right there. It just flattens out momentarily. But it's an increasing function otherwise. So if you're standing at this point, which is a critical value, by the way, that point is a critical point. It is neither above all values or below all values to the left or right. It's actually still climbing. So if you look to the left, yes, it's above values to the left, but it's below values to the right. So that is not a local extreme. Yet it is actually a critical point. So there's a good example of something that, or a point that is a critical point, but is not a local extreme. That can happen. It is true though that local extremes often are, it is true that critical points often lead to local extremes. They're not always local extremes. So let's do some mechanical mathematics here. Let's find the critical numbers of the function. Now remember, the critical numbers occur when f prime, or in this case h prime, is 0 or h prime does not exist. So that's what we're looking for. When does h prime equal 0, or when does h prime not exist? So obviously, first thing we need to do, find h prime. That's pretty easy, right? So this function will imply that h prime is equal to 3/4 t to the negative 1/4 minus 1/2 t to the negative 3/4. Well, we can immediately see that t equals 0 causes an issue because remember, negative exponents, those things belong downstairs, right? So if you want to combine these into a single fraction, you totally can, but that's not actually going to change anything about the domain issue here. So t cannot be 0 for the derivative. While it can be for the function h of t, you could totally have t be 0 there. The derivative is undefined at 0. So thus t equals 0 is a critical point, or a critical number, if you will. I kind of use those words interchangeably. So if I happen to say critical point and it's just x equals or t equals, just know that I mean critical number. I just have a habit of saying critical point. So this is where our derivative does not exist. Let's also take a look at other places our derivative doesn't exist. Well, think about the domain of the original function. Some people will argue that, oh, the derivative doesn't exist when t is negative, because if you look at this this derivative here, it's 3/4 times the 4th root of t minus 1/2 times, I'll just write this as t to the 3/4 because you get the point from this. T must be positive. Otherwise, you're taking the square root of a negative number, or 4th root of a negative number. But that turns out to be the domain restriction from the get-go. T, its domain is 0 to infinity. So really, I'm only considering values, input values starting at 0 and going to infinity. So I'm not really concerned about negative numbers here. All right, so that's just a little heads up about that. I'm going to erase this because it's kind of in my way. Now we want to solve h prime is equal to 0. Remember, you're really curious about when is h prime 0 or when does h prime not exist? Well, we've already found when h prime does not exist. So letting h prime equals 0, that will imply, if you can imagine this is 0 here, I'm just going to go ahead and add a half t to the negative 3/4 to both sides. And this would be 3/4. Actually, I think that it might be easier to do this problem in a different way than I'm looking at this. So I will. You know what I'm going to do? I'm going to do it a different way. I'm going to do it like this. 0 is equal to, I'll factor out a t to the negative 3/4, and I'll be left with 3/4 t to the, let's see, negative 1/4 plus 3/4 is 1/2 minus 1/2. Now, I did it that way because I want to reinforce your algebra factoring skills. So all I did here was factor out the lowest power of t to the negative 3/4. When you do that, you're actually adding 3/4 to all those powers on t. And so negative 1/4 plus 3/4 is 2/4. So that would end up being a t to the 1/2. And negative 3/4 plus 3/4, that's t to the 0th. So that's how I factor very quickly. You could see that what this becomes 0 when our second factor here is 0. So we're going to go ahead and say this implies that 3/4 t to the 1/2 must equal 1/2. Or in other words, multiply both sides by 4, divide both sides by 3, and you get t to the 1/2 is equal to, what is that, 2/3? And then square both sides. So t is equal to 4/9, squaring both sides. So we know that the derivative is going to be 0 at 4/9, which is in the domain of the original function. So we know that t equals 4/9 is a critical number. So there's our two critical numbers. If they ask for the critical value, like, okay, what are the critical numbers? And then what are their values? What's the value of the function there? Or what's the critical point? You would plug in those values into the original function to find what the points are. That is, the critical point associated with the critical number 0 is h of 0, which is 0. So the critical point would be 0, 0. And then if you were to plug in 4/9, it would be whatever h of 4/9 is, which I'm not really that concerned about finding right now. Okay, but that's how you would find the critical points if you were asked to find the critical points instead of just the critical values or the critical number. It's not my intent for this video to be so long, but the reality is that you can't really break this information up into smaller pieces very easily. So I'm just treating all this in a single video, but we're making our way through. We're not totally through, but we're making our way through. Find the critical numbers of this function. Again, you want to find out where f prime is equal to 0 or where f prime does not exist. Great. So let's first find f prime. F prime of theta is equal to a negative 18 sine of theta plus, this is a chain rule because it's a square of something. So the derivative of a square of something is twice that something to the first power. So that's 18 sine of theta to the first, and then times the derivative of sine, which is the cosine of theta. There you go. That's beautiful. And I love this problem because it involves trigonometry, which is critical for you to be super duper comfortable with as you move into Calc 2. So this derivative always exists because the domain of these functions are all real numbers. So we don't have to worry about that. But we can set that derivative to 0. We're going to solve f prime equals 0. We're going to find out how that becomes 0. You can see that both terms on the right hand side involve an 18, which I'm just factoring out a negative 18, sine of theta. And I'm left with a 1 minus cosine of theta. So the real question is, when is sine of theta equal to 0? And when is cosine of theta equal to 1? And from our trig, we know sine of theta is equal to 0 at any integer multiple of pi, and cosine is equal to 1 at any integer multiple of 2 pi, right? So because cosine's 1 at 0, at 2 pi, at 4 pi, and sine is 0 at 0 pi, 2 pi, and so on and so forth. These overlap, so you only need to really state the first one. And so critical numbers are theta is equal to n pi, where n is an element of the integers. It's just any constant multiple of any integer constant multiple of pi. Those are the critical numbers. The critical values you would plug in, it would actually alternate. So you would have 18 and negative 18. Those are the critical values. Not that big of a deal, but I suppose it's a moment to learn, right? That's what we call that. So you know that, for example, sine here, it turns into 0 at any integer multiple of pi. So that 9 sine squared, it's gone. But when you evaluate cosine at pi, at 0 pi, 1 pi, 2 pi, it alternates between 1 and negative 1, 1 and negative 1. So honestly, the critical points are going to be, how do I want to write this? If they wanted to have us write it. Well, I happen to know that the cosine becomes 1 at 0, 2 pi, 4 pi, 6 pi, basically any even multiple of pi. And so that'll become 1 times 18. And then at odd multiples of pi, so you could write this in a couple different ways. I'm actually going to write it just as 2n plus 1 pi. That's an odd number times pi. Odd multiples of pi, it becomes a negative 1, so negative 1 times 18 is a negative 18. Those are the critical points. Again, n is in the integers. It's a little bit more than they probably wanted, but it was a moment to learn. I had to pause the video for a moment here because I was trying to decide, do I want to prove this here? I actually have a proof of this elsewhere, but I think I might not prove it here just because of time. So this is Fermat's interior extremum theorem, although my textbook calls it Fermat's theorem, sadly, because Fermat's theorem is actually attributed to something else. But anyhow, if f has a local extreme at c, and if f prime exists, then f prime of c is 0. That is sort of what we were seeing with our examples earlier. If our derivative existed and we had a local extreme, so our derivative exists here and here, and we have a local extreme there and there, then the derivatives must be 0. Now notice that's only covering 2 cases, right? So there are other local extremes here, but if you have a local extreme and the derivative exists at that local extreme, then the derivative must be 0. The curve must have flattened out momentarily to give you that local extreme. And as I said, I have a video on the proof of this. I'll sneak it in after this or something like that. But this is a very powerful theorem because this allows you to work with graphs of functions and find when you have local extremes or not. Actually, really, it allows you to work with critical numbers and local extremes. It basically says that if you have a local extreme, and again, derivative exists, then f prime of c is 0. Now, the converse of that theorem is not true. Now, remember, the theorem was if you have a local extreme and the derivative exists, then the derivative is 0. So the converse would be f prime at c equals 0 implies, if it were true, which it's not, that f has a local max or min. But that's not true. But that would be the converse of Fermat's interior extremum theorem. But that's just not true. It's not true. Because I can give you graphs that have derivatives of 0, but that function does not reach a local extreme there. Right? So the derivative is 0, let's just pretend right there momentarily, but that's not a local extreme. So there's a good counter example. Also, if the derivative at c does not exist, then you just can't say anything. Fermat's theorem doesn't say anything at all. You could have a local extreme, but the derivative not existing means that The derivative doesn't exist. That's just it. And here's a very last theorem that we're going to talk about. This one's kind of a no-brainer, but if you have a function that has a local extreme, then c is a critical number of f. Let's talk about why that's true. Let's suppose that f has a local extreme at c. Let's just assume that, okay? Then it's pretty binary what's going to happen. Either f prime at c exists or it doesn't. So if f prime at c exists, well then, exists, then f prime of c must be 0 by Fermat's interior extremum theorem, and that will imply that c is a critical point, or critical number, I should say, right? There I go. I just did it, right? Where I said I will sometimes use the words critical point rather than critical number. Well, it's binary, so again, either the derivative exists or it doesn't. If f prime at c doesn't exist, well, then by definition, c is a critical number. There you go. We've proved it, actually. That happened very quickly. I wasn't considering proving that. That's why I didn't have the little proof thing there, but it just kind of fell out very quickly. So, having a local extreme means, or at c that is, means that c must be a critical number. So going back here, look at all the extremes. Local extreme at 1, 2, 4, 5, and 6. Those are our local extremes. And notice that all of those are critical numbers because the derivative doesn't exist at 1. It's 0 at 2. It's 0 at 4. It doesn't exist at 5. And it doesn't exist at 6. So again, local extremes give you critical numbers. But as I mentioned down here, critical numbers don't always give you local extremes. So the converse is not true. Now, for those who actually pay attention to my numbering scheme here, I didn't want to skip this, but we've actually talked about this. Must every continuous function have critical points on a closed interval? And the answer to that is no, they don't. And here's where that definition, by the way, gets a little blurred. If your instructor says that the endpoints of a closed interval are always critical points, then this is vacuously true. It's true because endpoints are always considered critical numbers. But that's why I dislike that endpoint definition, because then it makes this question very silly. Plus, it just doesn't work very well with the rest of mathematics. So, it is not true that every continuous function has a critical point, because you could just look at this. There's a closed interval, and I have a function that is differentiable the entire time, and its derivative is never 0. So there you go. There's a continuous function. It doesn't have critical points on a closed interval, according to my definition. On the other hand, is it possible for an increasing function to have a critical point? And the answer to that is heck yeah. This function right here, well, okay, that's not the right function, but y equals the cube root of x. Let's do that one. There's several examples, but this one will be fine. Y equals the cube root of x looks like this. I'm going to go ahead and just use red to graph it. Looks something like this. Something like that. It is an increasing function from left to right. It constantly, its derivative is, or it's always increasing. It's just increasing, always. However, if you take its derivative, it does not exist at 0. Y prime is equal to 1/3 x to the negative 2/3, and therefore the derivative does not exist at 0, and that is because it momentarily becomes vertical. Oops, wrong pen color, but it momentarily becomes vertical at x equals 0, so the derivative does not exist. And that is, by definition, a critical point. So there you go. There is an increasing function that does have a critical point at 0. And just for completeness, I wrote yes on that. So that actually wraps up the topics about local extrema. And that is actually the harder topic in this series of lectures, because it doesn't get used very quickly. So if you're working on a traditional calculus textbook, you're not really going to use local extrema continuously at first. It's going to take a little bit. Once we start actually using our calculus to do really, really good, accurate graphing, that's when we're really going to bring into this conversation local extrema. But for right now, it's a gateway so that we can talk about absolute or global extrema, which is important for our conversation.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much, that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.